In an earlier session, we discussed covalent bonds as based upon electrostatics, repulsions and attractions between electrons and nuclei. And in particular, we discussed the simplest molecule, hydrogen. And we discovered, as a result of these electrostatic repulsions and attractions, we generated in a covalent bond, which is a shared pair of electrons or more, we had particular lengths of these bonds and particular energies required to make them or break them. And they're listed on this table on the right, for instance. And also, in the table you see, it depends on particular atoms involved. And these atoms have particular sizes, and they have particular electronegativities. They have particular number of valence electrons, for instance. So, bonds, lengths, and energies. And we're going to discuss some of the common bonds here, and we're going to start by discussing the word of these tables that we need to always be looking for, patterns in the data. Now, when we look at a data table, and I will emphasize this lots of times, the first thing you do is you look at why the author put the table there. That's usually in the title or some descriptor. Chances are the author didn't put that table in the book at that point to impress you with, say, a particular color, such as, wow, look at that sky blue pink, that's a great color, or wow, he sure impressed me, or she impressed me with all those squiggly lines. So the why is something, when it says see table 32, that means really see it with your mind, just not with your quick vision. The second thing is find the variables in the table. Critical. What are the variables? There'll be letters, sometimes designations for these variables. And the variable in the table here, one variable is bond length, and the other variable is bond energy. The variables. The third thing is the measurement units. Measurement units. Now notice the measurement unit of nanometer, bond length. We usually use picometers. And the picometer is used because that's 1,000 times larger than number, and it becomes 74 picometers for hydrogen, 127 picometers for hydrogen chloride, etc. Also, the unit of kilojoules sometimes is kilocalories. The fourth thing we look at is the conditions. There are no conditions for this table. Conditions could be some standard condition, or perhaps some unusual conditions of temperature, pressure, etc. Also, the source of the data. Very important, where the data comes from originally. The fifth thing is really the meat and potatoes of the table, and that is trends. Trends within a column or between. For instance, if you look at nitrogen-nitrogen bonds, as you go from a single bond to a double to a triple, the bond length gets shorter, and the energy to, this is going between the variables now, the energy to associated with the forming or breaking of this bond gets greater. And you see the same trend with carbon-oxygen bonds. The fifth one, look for anomalies. Anomalies. I have no idea what that means. Maybe this is what you should do when teachers give you a word that you don't understand. Anomaly is really an outlier. Now, what is an outlier? An outlier is a possible exception to the pattern, something that doesn't seem to fit. Sometimes outliers are part of a deeper pattern. For instance, have you ever read the book Outliers by Malcolm, I think it's Gladwell? You see that sometimes outliers are part of deeper patterns. Sometimes they can be associated with error. For instance, if you have a group data table and your group calculated the density of aluminum as 19.3 grams per cubic centimeter, either you're on the way to a Nobel Prize, or perhaps you made a mistake that aluminum's density is not the same as gold. So check for errors. Now let's look how this data can be used. That's the next thing. Why is it there? Well, if you take hydrogen gas and chlorine gas, for instance, and we know we can write a reaction, HCl, let's apply the data to this reaction. Hydrogen is hydrogen-hydrogen bond. We have to break that. There is a chlorine-chlorine bond. We have to break that. And we have to form two hydrogen-chlorine bonds. That's the reaction. So if we look at the table, the energy required to break the hydrogen-hydrogen bond is, can you find that in the table? 435 kilojoules per mole to break the hydrogen. And to break the chlorine is 243 kilojoules per mole. That's energy in. Now the energy out is, when these bonds are formed, the energy given off, 431 kilojoules for hydrogen chloride, and we have another mole, 431 kilojoules. Energy in, energy out. So add these up. If you add them up, the energy out is greater than the energy in by 184 kilojoules. And we're going to write this down here. In this reaction, we have a net change of 184 kilojoules out. You may have learned if energy comes out of a reaction, it's called exothermic. There's heat coming out, 184 kilojoules. So we just now found how you can use the bond energies. I think we'll stop right there. And what you need to do is maybe go back to covalent bonds, hydrogen, to get into the basics of the bond formation.